Take off. right. Hello, everyone. Um, I've tinkered with some of the latency settings, so hopefully responses are going to be a little more live. Um, Also trying out to see if I can get closed captioning to work. Hopefully that'll work as well. I'm looking for feedback, so towards the end of the class, give me a shout if you have any sort of feedback. Um, all right. Hello, everyone. Welcome. So last class, we talked about Scala, and in particular, one of the things that we focused on was looking at Scala's collection capabilities, collection transformation capabilities. I want you to, for those of you who are here on Thursday, I want you to think back to that part of the lecture and just kind of have that in the back of your mind throughout the entire class. For those of you who are already familiar with Scala and may not have been there on Thursday, I want you to be thinking of map, filter, flatten, all of that stuff over the course of the entire lecture. The terminology is going to be different, but the ideas are going to be almost identical. Okay, so over the course of the last, over the course of Tuesday, I brought up this idea that pretty much the entire class or each segment of the class could be summarized by, we're going to take thing A that the user asks us to do, and we're going to replace it with a better but equivalent thing B. And so in order to do this, we essentially had to answer two questions. So first off, what is the space of allowable thing Bs? Like what is, if we're trying to come up with a better algorithm or a better implementation of what the user is asking us to do, we actually need to know what our design space is. So first question we need to answer is what that design space is. And once we have that, then we need to be able to figure out which point in that design space actually is the right one given the specific requirements of the user, the constraints. Let me bump up the volume a little. Is this better? Hopefully this is working. If not, give me a shout in the chat. Okay, so to repeat, the goal of the class is to be able to replace something that the user asks us to do with an equivalent but a better version of that. So, okay, in order to do that, we need to be able to answer two questions. Well, first off, what is the design space that we're allowed to explore, given something? What are the viable replacement candidates for it? And once we know what the viable replacement candidates are, then how do we know which of those is the best, or how do we compare two different options? Okay, today and for the first couple of classes, we're specifically going to be looking at query processing. So the user poses to us a question in some language, and we're going to take that question and restructure it, rephrase it, tie it down to some specific algorithm, and then essentially how do we figure out what are the equivalent algorithms that can be used to answer that question, and how do we know which of those algorithms is going to be the most efficient? Before we get to that, and sorry, to our kind of the overarching theme of this lecture is going to be to set up a framework that we can use to answer that question. We're not going to answer it completely today, but over the course of this week, at least we'll have some sort of kind of framework in which we can discuss the answers to these two questions. But before we get to that, I just want to recap a couple of definitions from last Tuesday. And the first of those, I'm going to use the term relation and table alternatively to refer to a collection of tuples of primitive values. And all of those tuples have, I'm expecting that all of those tuples have exactly the same type attribute types, or in other words, schema. It's also customary to give each of those attributes a name. So I'm expecting that all of the tuples have the same names. As we talked about last As we talked about last Thursday, apologies for the closed captioning. I saw some settings. I thought there might have been a way to get YouTube to automatically close caption it. If it's not doing it, then apparently that is not a thing that YouTube does in live streams. I will keep investigating, but well, the post recording should be closed captioned at least. Okay, so as we talked about last Tuesday, there's essentially three types of collections that we're going to be working with. And the simplest of these is the bag. Just it's an arbitrary collection. There's a bunch of tuples, nothing fancy about it. And then there's two restrictions of bags, sets, which are bags, but we're not allowed to have duplicate values, and lists, which are bags, but the order of the elements in the bag actually matters. So, for example, they might be in sorted order on one of the attributes. Okay, so we talked about different types of collections and types. Another thing I want to bring up is or create a contrast with is declarative languages. I want to contrast declarative languages specifically with the more imperative languages that you might be more familiar with. And the main difference here is that in a declarative language, you essentially say what you want as opposed to providing a specific algorithm like you would in an imperative language. So if you're writing a piece of code in C, you need to kind of go step by step and express literally how the data is transformed one step at a time. Whereas in a declarative language, you provide your goals as more high-level constraints on the result. For example, you just tell the system, get me the TPS reports, as opposed to actually, saying, get me every T report, and then for each week sum up the number of sprockets, find the corresponding S report, blah, 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 blah. Now, the reason I want to make this contrast is that in a declarative language, it's a lot easier to find equivalent computations. And remember, that's kind of our goal for today. We want to come up with a framework that allows us to look at all of the design space of equivalent computations so that we can, equivalent algorithms, excuse me, so that we can find the best one for our particular use case. To give you an even more precise example of this contrast, in SQL, I might say select RA from R comma S, where RB equals SB and SC equals 10. So here I'm essentially putting some constraints. I'm telling the system which data sets I want to look at, R and S. I'm telling the system how I want these paired up, RB equals SB, and I'm also putting some additional constraints on the solution. I'm only interested in pairs where SC is 10. And then I'm also telling it what specific outputs I want, R.A. And if I write this code in Python, there's a couple of additional things that I need to embed in the solution. And first and foremost, I actually need to provide a very specific algorithm for solving the problem. So for example, in this implementation, I'm literally looping over all of the records in both data sets, and I, that may not necessarily be the most efficient way of doing it. And if any of my constraints change, I may need to completely re-engineer all of my code. Another subtle but also important thing to bear in mind here is that I also need to know the data layout. So if I'm writing this in Python, I need to know the attribute, the specific position that an attribute appears in. I need to know the format, the type information of each attribute, and I need to know how the data is stored. So the Python code is specifically referring to CSV files. And all of that is kind of abstracted away in the SQL. I don't really need to think about how the data is stored, how the data is laid out, because all I'm specifying is what I want, and then the system can kind of figure out how to achieve that goal. So for query languages, there's a couple of different uh, declarative languages that we could potentially use as a model or as a framework for reasoning about equivalent queries. There's SQL, as we've seen, and then there's relational algebra and relational calculus. Now, SQL was designed largely with a focus on readability, on user friendliness. And because of that, there's a lot of corner cases, there's a lot of structural weirdnesses that are essentially just there to make it easier for humans to interact with. And the downside for that is that it also makes it a lot harder to for computers to interact with that same structure. Relational algebra is an equivalent thing to SQL. It's structurally, in terms of expressiveness, there's nuances, but for the most part, relational algebra, anything that you can express in SQL 92, you can express in some flavor of relational algebra. And relational algebra essentially looks at data flow. So how does data go through, what kind of transformations is it subjected to as it achieves a particular query result? Um, Relational calculus is kind of a simpler, more mathematical way of modeling expressions. And here the idea is mainly to look at interrelationships between attributes. So these are kind of the three most common ways of expressing queries declaratively. Now we've already seen SQL. Here's exactly the same query, select RA, where SC equals 10 and RB equals SB, but phrased in relational algebra. And throughout the course, you'll see me using two different notations for relational algebra. This sort of tree-like structure where the answer or the output to the query is at the top of the tree, right here. Um, so you can kind of think of the result coming out from there, and then the input tables are at the bottom of the tree, and they kind of feed into this data flow graph. So often I will use this sort of tree style representation, but there's also a little more mathy representation of exactly the same thing, where each operator is just a function. You can look at it as a function. So the join, or this operator here that looks like a bow tie, reads in both R and S. So the analog here is that you have the bow tie operator, and it is a function applied to both inputs. Okay, so the right, so relational algebra. We'll go in. You don't need to kind of take away all that much just apart from the general structure of it, but want to give you kind of an initial flavor of what relational algebra looks like. Relational calculus, or its close relative data log, would express exactly the same query this way. So I've got a query and I've got a particular output attribute, and then I'm reading from two tables, R and SB, and the fact that B appears the same in both of those queries means that I'm essentially looking for pairs. Right. So this kind of gives you a general sense of the flavor of these three languages. And the one that we're going to be focusing on this semester, we'll get back to relational calculus. SQL is always going to kind of be in the background because that's what the user is creating. But what we will be using for the first part of this semester is relational algebra. This is both because that data flow graph, that data flow representation makes it really nice for kind of reasoning about algorithms and reasoning about how the query is computed, but also because this is how Spark internally represents its queries. And towards the end of the lecture, the first part of the lecture, or the bulk of the lecture, is going to be talking about relational algebra itself, but then I'm going to kind of go back and show you some source code from Spark itself to actually show you that there's pretty much a literal one-to-one mapping between what I am describing today and what is actually implemented in Spark itself. Okay, I keep talking about relational algebra, I keep talking about, but few more bits of background. So at least for the first half of this course, we are going to be talking about fixed data sets. So I have a data set, a bunch of CSV files, a bunch of tables in a database, whatever. I have my data up front. It has a known structure, so I know the attributes of each table. I know the data types of each table. In other words, I know the schema of the table. And that table has a fixed collection of rows. Towards the second half of the term, we'll talk about, well, how do you deal with data that's changing over time? And there's some interesting things that we can do there as well. Okay, so when I pose a query, I'm going to think of that query as essentially a function that is applied to a bunch of relations. So for example, I might have a query where I ask some question, and the inputs to this question are going to be a couple of tables, like for example, the trees table and information about tree species. And one important thing to note is that in relational algebra, the output of a query is just a table as well. If I pose a query over trees, for example, I do some transformation over trees, I can take the output of that query and I can just feed it right back into a new query. Kind of the technical term for this is that relational algebra is closed. Okay, before we get into it, are there any questions so far? All right, not seeing any questions at the moment. I will in a moment have some questions for you, so folks can start waking up. Okay, relational algebra. Relational algebra is essentially composed of a set of very simple operators. Oh, can I repeat the last term? Relational algebra? Or relational algebra is closed over relations. In other words, it just means that the output has the same format as the input. You don't need to memorize that. It just, for anyone who is familiar with the term closed, there you have it. Okay, so relational algebra is composed of a set of basic operators. And because it is closed, because you can apply operators to the output of another operator, um, you can essentially build up a pretty wide array of different computations over collections by combining these individual primitive operators. And there's 5 basic primitive operations: selection, projection, cross product, set difference, union. You don't need to memorize this right here. We'll go into a little more depth in just a moment. But I just wanted to kind of put all of these things into one table, just as a reference for you for later. In addition to these basic operators, there's also a couple of composite operators: intersection, join, division, renaming, that don't really give you any new expressive power, but that are convenient for one reason or another. And we'll talk about we'll talk about a few of these in just a moment as well. These additional operators are, like I said, not critical, but they can be useful. Okay. Now, I've been hand waving at least one thing so far. I said at the beginning of the lecture that we're working with 3 different types of collections: sets, bags, and lists. And accordingly, I've only been kind of talking about one relational algebra. and that's a little bit of a lie. Um, so uh, if so it's important when talking about relational algebra to talk about the data model as well, which particular form of data you're working with. So for example, if we are working with sets, or in other words, if the input to my query is a set and I want the output to be a set as well, then I am working with set relational algebra. If you talk to theoreticians, they will just call this just relational algebra. Um, I will try and avoid that. If I ever use just relational algebra, and I'm not talking about all three of these classes, then please yell at me. Um, if we're working with bags, similarly, the input, if the input is a bag, and I expect to see a bag as an output, talking about bag relational algebra. Anyone want to take a guess at what the third of these is? List relational algebra. Harsh, you are very active here. Lists. Okay, well, that was a little bit of a trick question. We call it extended relational algebra. Um, yeah, I know. Um, at any rate, we'll get back to extended relational algebra because there's a couple of additional complexities that come up when we're dealing with order. We have to keep track of, we have to be able to manipulate that order, sort things, mumble. So we're going to talk about extended relational algebra in a couple of classes. For now, we're going to focus specifically on set relational algebra and bag relational algebra. Okay, so selection. Um, you Selection is analogous to the filter operation in Scala, and it's essentially you provided a condition and it returns the rows that pass that condition for which that condition evaluates to true. Usually we write selection with a lowercase sigma and put the condition as a subscript on that sigma. So for example, I might write this query here to pick out all of the trees that appear in the borough of Brooklyn. Um, and selection, well, maybe not surprisingly, is analogous to the where clause in SQL. So if I was translating from SQL to relational algebra, essentially the where clause would just become a selection operator. Um, Projection, usually written with a lowercase pi and subscripted with one or more attributes, is essentially going to produce an output that contains only those attributes. All of the other attributes just get thrown away. So for example, if I wanted to get the trees, if I wanted to get the borough name attribute of all of the trees, table, excuse me, write this query, and I would get an output. Okay, so here's an output. Does anyone see something maybe a little bit funny about this? It outputs just a single column. Okay. There's one. Select unique. Okay. So there's this output only contains 5 results. The trees table has 600, nearly 700,000 results. Why am I not seeing all of these? And um, this kind of gets me to the point why it's important to distinguish between set and bag operations. Not necessarily for every operator. We'll come back to that in a bit, but If we're looking at projection, then we need to keep track of whether we are talking about set projection or bag projection. If we're doing set projection, then all of the outputs had better be distinct. And if we are doing bag projection, then we expect the output to be, then we essentially get one row for every input row. Again, to map this back to SQL, projection is essentially the target list. If I put a set of targets in my query, that essentially just gets turned into a projection on top of the query. And if I provide a distinct, if I use the distinct keyword, that's essentially signaling to the SQL interpreter that I am working with set projection. Okay, so like I mentioned earlier, the input, if the input to one of these operators is a relation of some sort, set, bag, or list, then the output is also a relation. And the inputs, input relations all have schemas. They all have attribute names, types as well. We're going to ignore types for just the moment. The output had better also have a schema. So here's a query. What is the output schema for this query? And I'm going to hope by the time the stream catches up, someone will have answered. ID, tree name, city name, perfect. Here's another one. What about this one? And you know what? Let's cut down on lag. Here is another one. So for the first one, I'm seeing some responses. Yes, tree ID, SBC common, and burrow name is the schema of the first of these queries. So to be clear, what I'm asking for here is the schema. What are the attributes that appear in each of these queries? So for select burrow name equals Brooklyn, yes, okay, Srishti, good. You're returning all of the attributes for the trees. So selection doesn't actually change the schema of the output table. I'm specifically looking here for all of the attributes and just filtering on a specific subset. And the third one, similarly, is returning all of the attributes of the input to the selection, but the input of the selection here, remember, we can compose queries. So the input to the selection here has the schema tree ID, SBC common, and burrow name. So the third query is going to return just those three attributes. Okay, so we talked about selection and we talked about projection. Now let's introduce union. So union is going to take two relations. Yes, perfect, Nuraf. The union is going to take two relations that are what I call union compatible. In other words, they have the same number of fields, those fields have the same types, those fields have the same name, and it's going to return all of the tuples that appear in either of the two input relations. So for example, I might ask in the chat, I'll keep going, but in the chat, please, what is this query here asking in English? Give you a moment to respond. Okay, so you might also see me use a little plus sign in the middle of the union symbol, and union symbol is basically just a big U. Uh, the the union is if I put a little plus symbol in there, that is basically me saying I'm specifically referring to bag union. Okay, so the next one is the next operator is intersection. So once again, I'm expecting both inputs to be union compatible. Yes, Johan, good. Exactly. I'm asking for all of the Brooklyn and Manhattan data. Okay, so intersection is going to take two union compatible inputs and give me all of the records that appear appear in both of them. So it has to appear both on the left and the right hand side, but otherwise it's pretty much the same. So here's another query. I'll give you a moment or two. Wait for the stream to catch up, and then what is this query here asking for? Uh, so there's a question here. Is the union operator in relational algebra equivalent to union or union all from Usam? So that's a great question. And in relational algebra, it depends on which of the two relational algebras we are working with. If we're working with set relational algebra, or in other words, if we're talking about set union, then it is essentially equivalent to union distinct or just union in SQL. If we're working with bag relational algebra, or we're talking about bag union, then we're talking about union all. Yeah, so can we produce a set? Do we produce a set as the output, or do we produce a bag as output? Elizabeth, perfect. So these are the tree species that appear in both Brooklyn and Manhattan. Great. Okay, set difference. So set difference is also going to take two union compatible tables as inputs, and it's going to produce all of the tuples that appear in the first of the left-hand side relation, but that do not appear in the right-hand side relation. So once again, I'll ask, what is this query here asking? And set difference is just a minus sign. Give folks a moment there. And Elizabeth, yes, perfect. Trees in Brooklyn that are only in Brooklyn, but not Manhattan. Perfect. Okay, so for union, intersection, and set difference, what is the schema of these operators? All right, hopefully the stream will catch up there. Um, okay, so we talked about union, we talked about set difference, and we talked about intersection. We also talked about selection and projection. Schema of any. Okay, great. So basically, with union and as well as intersection and set difference, the operators are only defined if the inputs have the same schema as each other. So yeah, the same Deepak. The output is uh, is just that schema. Um, All right. So we talked about union. We talked about the union compatible operators. We talked about selection projection. Now let's talk about Cartesian product. So this is probably outside of SQL. This is not very frequently used. But in SQL, it is incredibly powerful for reasons we'll get into a bit later in the class. Uh, so Cartesian product essentially takes two different tables. Now union takes the two tables and essentially stacks them on top of each other. It just takes all the rows and concatenates all the rows, deduplicating if we're talking about set union. Cartesian product is instead going to take the two and put them side by side. So specifically, we're going to take every tuple in one of the two tables, and we're going to pair it up with all of the tuples in the other table. So, well, not surprisingly, for every row in the if we have n rows on the left-hand side, then for every row on the right-hand side, we're going to produce n rows of output. So to give you an example, if you're having difficulty visualizing this, I certainly do. Um, so if I have the tree info table and the trees, and I'm trying to compute a Cartesian product of two attributes from the tree info table and two attributes from the trees table, then essentially what I'm going to do is for the first row of the tree info table, I'm going to pair it up with every single row of the trees table. And you can see that here. And then I'm going to take the next row of the tree info table and pair it up with every single one of the inputs from the trees table. And I'm going to keep doing this until I get to, and I'm just going to keep doing this until I get to the end of the tree info table. So literally every possible pairing of these, the Cartesian product creates every possible pairing of tuples from the two input relations. I'm going to pause here very briefly for questions. Okay, not seeing any questions yet. Maybe they will catch up in the stream, but let's move on. So let me ask you a question. If I have a Cartesian product, so I'm taking these two attributes from the trees table and these two attributes from the tree info table, what is the schema of the resulting table? Okay. Priyanka asks, do we need to have any common column for the cross product? Fantastic question. So for a Cartesian product, the answer is no, but you're leading a very interesting thing that you can do with Cartesian products that we will get to in just a moment. All columns from both of the tables. Yep. So if I take, yes, Adish, perfect. So you take all of the columns that are in the left-hand side and all of the columns in the right-hand side, and you smush them together, and that's the schema of the result. SBC common, row name, SBC common, average height. And now here maybe you are noticing that there is something weird here because the field SBC common appears in both of these tables. So what do we do about that? Well, that is where the renaming operator comes in. So renaming doesn't really give you any expressive power, but for people's sanity, it got introduced to relational algebra. It really doesn't actually do anything meaningful. But it's handy to be able to just say, okay, now in the plan, I'm going to refer to the attributes of this table by new names. So for example, here, a renaming operator just takes a subscript, as a subscript, it takes a list of attribute names that has to be the same number of attributes that appear in the input table and in the same order. Amneet asks, well, let me ask you first, what is the schema of this resulting relation? And while you are answering that question and while the stream catches up, Amneet asks, so Cartesian product isn't similar to joins in SQL. You're on to exactly the same question as Priyanka, and you're leading me by about one slide. Um, But before I get to that other slide, I just want to emphasize one point. I want to make a distinction between formal relational algebra and the shorthands that I will take on the board over the course of the class. As far as formal relational algebra is concerned, as far as what I'm going to expect of you in homework assignments and on exams, the schema of a cross product is all of the attributes that appear on the left-hand side and the right-hand side. SPC common, borough name, SPC common, average height. On the board, however, that is going to get monotonous very fast. So instead, I'm just going to use a couple of shorthands, but I want to make it absolutely clear that the correct way to do this, the way I'm going to expect to see in exams and homeworks, is that the cross product produces all of the attributes as an output. And yes, Jeshta, again, apologies for name issues, but yes, you've got it perfectly. So the T name, borough, I name, and average height will be is going to be the output schema. Okay, Priyanka and Amneet, you led me by a couple of slides there with your questions. So let me answer you completely. There is another operator that is often convenient. Now, cross product or Cartesian product is going to give you all of the possible pairs. So every single attribute from the left-hand side paired up with every single attribute from the right-hand side. But often what you want to do isn't pair up come up with all of the pairs. More often what you care about is coming up with with very specific pairs or pairs that satisfy some specific condition. For example, in this particular case, maybe I'm interested, it doesn't really make sense to pair up all of the trees with all of the bits of tree info. What I'm actually more likely asking for here is pairing up all of the trees with a lookup of the tree info for the corresponding tree. And I can express that by applying a specific variant of a Cartesian product, more commonly called a join. And a join uses this funky symbol that looks kind of like a bow tie, and it has a subscript like the selection operator. The join operator you put the condition of the join as a subscript. And similar to the selection operator, this is a point I'm going to come back to next lecture, but the join operator is literally the same thing. In terms of what it computes, it is literally the same thing as coming up with all of the pairs of tuples, everything on the left-hand side paired with everything on the right-hand side, and then just filtering out the pairs that satisfy the specific predicate. Now, if you know that it's a join, you can be a lot more efficient, but in terms of the output and what we mean by the output being correct, both of these are identical. So more generally, if I have a join between two tables R and S on some condition C, that is completely equivalent to a selection of applying a selection predicate to our Cartesian product S. Karan asks, which of these two is more efficient? Well, if you know that you are looking for a specific subset of the pairs, and this is a theme that I'm going to come back to a couple of times over the course of the class, getting rid of data as early as possible is going to make your computation more efficient. So usually the more data you have, the slower or the longer it takes to process that data. So if you can come up with tricks to cut down on the amount of data that you have to work with, then it will be more, it will produce outputs faster. So similarly, if you can come up with some tricks that you don't actually have to generate all of those pairs, which you could do if you know that something is a join, then you can hypothetically evaluate the first of these queries a bit more efficiently. Great question. Great question, Karan. Yeshi asks, what is the difference between selection and projection? Also a good question. So you can think of projection as removing columns and selection as removing rows. Selection, you give it a constraint and it picks out rows that satisfy the constraint. Projection, you give it a set of columns or attributes and it gives you only those attributes in the output. Community asks, can the Cartesian product have duplicate rows? Johan already answered that, but hold that thought. We'll come back to it in a couple of slides. Okay, great. Oh man, Johan, you're a couple of slides ahead of me. This is fantastic. Okay, but before we get to that, I want to talk about one more bit of notation with respect to joins. So because they are so common, a very common way to use joins is to do lookups on other tables to find the corresponding items that are, in the example I gave you earlier, I'm essentially looking for the tree info for the tree that I'm currently querying. And we have a special name for this. We call it an equijoin. A join where all of our conditions, sometimes we call them predicates, are equality tests. A equals B. So because these are so common, there's a couple of notational shorthands that we will often use. If I have a particular attribute that appears in both of my input tables, and I want to do an equijoin on that attribute, then I will just write that attribute rather than spelling out the full equals. So R bow tie subscript A S is exactly the same thing, or what I mean is exactly the same thing is if I write R bow tie R A equals SA S. So I'm essentially doing a lookup. I'm computing all of the pairs that have the same value for that specific attribute. And if I want to be really, really lazy, I do what is called a natural join, where I don't provide any condition. And the implicit assumption here is that if I don't give you a condition, I am doing an equijoin on all of the attributes that appear in both of the two tables. So in the previous example, I could express that as a natural join because the only attribute that appeared in both tables was SPC common. Right, so a natural join is just a join on all of the attributes an equijoin on all of the attributes that appear in both tables. And I'm going to come back to this because I always get people asking, so I'm going to emphasize it here, and I will probably answer one or two more times over the course of the semester. But formally, what I expect to see in homework assignments, what I expect to see in exams, and what you should do when you are implementing things, the output schema of a join always has all of the attributes that show up in the inputs. Like Cartesian product, every single attribute, every single copy of every single attribute appears in the output as well. However, to save board space and to keep our sanity when discussing things at a high level, I will often collapse the attribute. So if I do a natural join, I might just write the output without creating copies of attributes. Harsh asks, which of these is more efficient, left or right hand side? So here, this is notational shorthand. Both of these are expressing exactly the same computation. There's no difference in information content. The left one just takes fewer pen strokes or keystrokes to write. Okay, so there's already some discussion about this in the chat. That is fantastic. I want to recap this for the class, but I guess maybe we already talked about this. I don't need to go into it. Um, but here's a bunch of so let's look at each of the operators and ask ourselves, well, can this operator create duplicates? Or in other words, if the input to one of these operators is a set, um, could the output hypothetically end up being a bag? So before I get into that, let me quickly answer Sukya's question. So the joins can be applied to multiple tables, right? Yes. So a join is always applied to two tables at once. You've got a left-hand side and a right-hand side, and you can also chain joins together. If you want to think of a join as being applied to many tables at once, that is a fantastic way of looking at things. We will get back to that next lecture. Um, okay, so selection. Selection, well, you're always removing tuples. If your input has no duplicates, I'm sure not going to create new duplicates by deleting tuples. Projection. So here's a little bit of a freebie because we already talked about it. So projection, on the other hand, if I'm removing tuples, sorry, if I'm removing attributes, then I run the risk of essentially removing the only thing that makes two different tuples distinct. So even if the two tuples are distinct with attributes A and B, if I remove B, now they might still have the same A. So if I'm implementing projection, there I do actually need to pay attention to whether or not I'm working with set or bag relational algebra. Cross product. So here, Johan has already answered me ahead of the slide. Cross product, in general, if the input has duplicates, well, the output obviously can also have duplicates. But if the input does not have duplicates, if the input is a set, then the output actually is going to end up not being a set either. Set difference follows the same thing as selection. If I don't have duplicates in my input, then removing tuples is not going to introduce new duplicates. Union, so we also already talked about this. Union can create duplicates. Now I want to ask you, what about join? So can join create duplicates? And why? Taking everything else that I've given to you as fact, can joins create duplicates? And if so, why? Karan asks, can I explain projection again? So projection is, I give projection a list of attributes, and the output table is literally just the table of the table that contains just those attributes. You can think of that as essentially, so projection is a close analog to map. I'm essentially applying a function to every record in my input, and I'm producing an output that consists of just the attributes that appear in the subscript. We'll get to some of this introduces a couple of extra nuances, so we'll get to it a little bit later. When we talk about extended relational algebra. But another way of thinking about projection is that this is the target clause of a select statement. So select, okay, good question. So how does it create duplicate values? So this is a good place for a little bit of an example. So we've got let's say we have a table, A, B, 1, 2, 3, 4, 1, 4. Now, this input over here is a set. Every single record in this input is unique. 1, 2 is distinct from 3, 4 is distinct from 1, 4. But if I do a projection down to A on this input, which is the same as writing project down to A of R, what I get is going to be 1, 3, 1. So essentially what I've done is I've gotten rid of the one thing that makes tuple 1 distinct from tuple 3. And so by removing that one distinguishing feature, now I have two tuples that are the same. So hopefully I've answered that question, Kron. If I haven't, give me a shout. Okay, people ask, or people are saying that joins do not create duplicate values. Now, I could simply say that, but I'm actually going to give you an informal proof based on asserting that the previous things that I've told you are true as well. So for example, if, so join is essentially, as we've established, a join is exactly the same thing as a selection and a cross product. I do a selection on top of a cross product. And cross product can't introduce any new duplicate values. Selection can't introduce any new duplicate values. So if my inputs to the cross product are sets, then my output is going to be a set. And that means the input to my selection is going to be a set, and the output is also going to be a set. In other words, because I already know, I can already prove this for selection, or I've given you, I've asserted that selection and cross product don't create duplicates. You can use that information to prove to yourself that join also will not create duplicate values. It's a little bit of a taste of what we'll talk about on Thursday. Okay, I was hoping to be a little bit further along today than I was. This will get turned into homework. Or not homework, but we'll do a variant of this as homework. Oh, hey, we've already asked this. So kind of to get you thinking about the same problem in slightly different way, well, what if, so here's two different variants of a query, and I'm going to assert to you that both of them are the same. We'll talk about how I can assert that on Thursday, but I'm going to assert to you that both of these are the same. And it may help to actually see them drawn out. So we've got a projection here sitting on top of a selection, sitting on top of a join between two tables. And then we have a query that I'm going to assert to you is producing exactly the same result that looks instead like this. Which of these two do you think will be faster? And I've already given you the information this class to answer that. The second is faster. Why? Hopefully someone will have answered by this point. But essentially selection is getting rid of tuples. And exactly, Deepak, perfect. So the second query removes data earlier in the process. So when we get to the join, joins typically end up being slightly heavier weight. Once we get to the join, we've gotten rid of more data. And so the join can be processed faster. Perfect. Okay, division. I'm gonna jump through this. I don't really enjoy teaching division because I've been working in databases for 20, 30 years now, and I have 20 years, uh, and I've never really encountered a situation where I need division. But this is the kind of thing that that shows up in interview questions. People see you've taken a database class, they kind of expect you to know this. So division is a operator that you can kind of think of as an inverse join. And I've yet to find a good way of explaining this just through definition. It's a lot easier to think about in terms of examples. So division is essentially going to take the table that's on the left-hand side and find all of the attributes that are paired with the corresponding attributes on the right-hand side. That's a mouthful. So For example, if I were to divide by a table that had one attribute, SPC common, honey locust, um, the division operator would return to me every single burrow, so all of the other attributes, in this case burrow, that have honey locust in the left-hand side table. So in this case, Brooklyn, Manhattan, Queens, and the Bronx all have are all paired with honey locust, so that would be the result of my division. If I divided by the table honey locust and American linden, I'm only going to return the boroughs that are paired with both of those. In this case, Brooklyn, Manhattan, and Queens. And if I restrict that, if I go to pin oak, I'm going to return all of the boroughs that have all of those attributes represented. In this case, just Manhattan. Um, Again, I have never seen division actually used outside of a interview question type thing, but there you have it. Jeshta asks, is it safe to assume that the optimization speed efficiency is directly related to the amount of rows being processed? That is a fantastic question. We will come back to this in a couple of, uh, we will come back to this in a couple of lectures. There's a lot of different things that go into it. The number of rows being processed is one factor. The actual volume of data is another. The number of attributes is another factor. There's considerations in terms of how much memory you have, what the different levels of cache you have. There's a ton of different factors. But when it all comes down to it, the number of rows actually ends up being a pretty good approximation. It doesn't get you to perfect to perfect, but it'll get to you to within some meaningful level of perfect in terms of optimization. Karan asks if you could do this by doing a join on SPC common equals honey locust. No, um, because what we're looking for is not the pairs. So we're not looking for the burrows that have honey locusts specific. Well, okay, the first, you're right, that the first division could actually be expressed as a two-way join. The other two, on the other hand, could not. You'd have to come up with a slightly more extensive query. It's a common question in other database classes and previous incarnations. I don't do this anymore, but previous incarnations of my database class, I'd ask, well, how do you implement division using other relational operators? It's going to do this as group work, but we have 15 minutes, and there's one other thing I want to get to before the end of class. So we'll come back to this another time. I'll post it on Piazza if anyone wants to kind of get some brag points. Um, but okay, so I've so far talked to you about relational algebra in a fairly abstract sense, very mathy representation of the queries. Now I actually want to tie that back to practice. And before I do that, I want to define one particular term. If you haven't heard it, an abstract syntax tree. So an abstract syntax tree is just a tree-shaped representation of a computation. And as you've already seen, relational algebra can be viewed as a tree, and it certainly expresses a computation. So relational algebra is one example of an abstract syntax tree. Amneet asks, division is done on the same relation, so you have two different relations. You've got a left-hand side and a right-hand side. The left-hand side is the bigger of the two. The right-hand side is the one that gives you the tables that the attributes that you're looking to match up with the left-hand side. Okay, so abstract syntax trees. And like I said, relational algebra is essentially a way of representing SQL queries, is one abstract syntax tree encoding of queries. And what I want to talk about to you right now is how Spark specifically uses abstract syntax trees. And in particular, there are two mumble, mumble, mumble. Um, for our purposes here, there are two abstract syntax trees in Spark, specifically in Spark Catalyst. Um, there is a class called expression. Talk a little bit about that today, and then more next week when we talk about checkpoint one. So expression, the expression abstract syntax tree encodes primitive valued expressions, or as Spark calls them, literals, or literal valued expressions. And then logical plan is the other one, which is, as you'll see in just a moment, a very close analog of relational algebra. It has a couple of other things packed in there. For the most part, we'll sweep those off to the side. Spark SQL, for the most part, uses a combination of BAG and extended relational algebra. So for today, we haven't talked about extended relational algebra, so I'm just going to talk to you about how BAG relational algebra maps onto Spark. But before we do that, I want to present abstract syntax trees in a slightly simpler context, because while you've only just been introduced to running a selection over a projection over a cross product over blah, 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 everyone here, I'm willing to bet, knows how to deal with 1 plus 1. I should hope so. Um, and that's the sort of thing that is encoded in expressions. A plus 1 would be encoded as an expression. And so the expression class, and we'll go into this in a lot more depth next week, but it provides a couple of interesting and useful ways of getting information about what the expression is and how it works. But the one thing for today that I want to bring your attention to is this tree node class. So tree node is essentially the base class in Spark for abstract syntax trees. And as it encodes a tree, there's a bunch of things that you'd expect. So you can get the children of the node. You can transform the children of the node. You can get a convenient string representation of the tree. And this is fantastic for debugging. And there's also this transform function. Now you're looking at this, you may not be familiar with Scala, and you're looking at this and seeing a partial function. What the heck is that? How am I going to deal with this? Well, a partial function, because this is going to show up in a couple of different places, I want to define it. A partial function is essentially kind of a combination of a lambda function, in other words, you inline define some sort of function, and a match statement. So you're essentially taking the input and then immediately matching it. And the reason it is a partial function and not a full function is that there's an expectation that you're not covering every single case. And so the unmatched cases are going to look a little bit like, are going to should be handled gracefully by whatever you're passing in. So for example, this transform operation is essentially going to go down the entire tree, and it allows you to provide a simple pattern match rule, set of pattern match rules that replace every occurrence of a particular pattern in the tree with a different pattern. So for example, here I'm matching on literal expressions and I'm replacing them with a new literal. And the idea, the reason it is a partial function, is that you don't have to provide the default behavior, because there's a fairly obvious default here, which is if you don't match the pattern, you don't change the node. I'm skimming over this really fast. I promise I will come back to it on Thursday. We are almost out of time. So for example, if I wanted to take every literal in an expression tree, if I had the expression a plus 1, I could apply a transform to it and replace every literal integer with the next highest integer. So if I started out with a plus 1 and ran this piece of code on it, what I would end up with is the expression a plus 2. This is only here to give you an initial exposure to it. Again, we will talk about it in a lot more depth on next Tuesday. Okay, expressions out of the way. Spark encodes encodes pretty much everything in relational algebra and then some. So this class called LogicalPlan, we'll see a couple of things here, and then we'll go into a little more depth on Thursday and next Tuesday. Um, it encodes relational algebra nodes pretty much directly. There's a bunch of other goop in there for handling JSON, machine learning, and a bunch of other things that are encoded as logical plan operators. Um, don't worry about those. For the purposes of this class, we're going to largely limit ourselves to the relational algebra nodes. There is also, for some reason, I'm not completely certain I understand the design decision here, but anything that you can parse, any SQL statement that you can parse, also gets encoded as a logical plan. This does make certain things in the parser, in the analysis phase, a little bit easier. It means there's reasons for this, I suspect, but those are also there. But for our discussion right now, and for the most part in this class, we're only interested in the case classes that encode relational algebra. Now there's two specific plans here. I have links to, if you go to the slides, I have links to these at the bottom of each page. Um, the it really is useful to have at least a quick glance at some of these. Now, Logical Plan has a bunch of stuff in it. For the most part, the only thing interesting in Logical Plan, the Logical Plan definition itself, is this query plan thing. Um, Spark actually supports a couple of different types of plans, logical plans, physical plans. I'm going to sweep that all under the rug for the moment. But the takeaway here is that most of the interesting logic for logical plans actually lives in this other class called query plan. So QueryPlan has kind of a couple of useful functions, and we'll go over these in greater depth on next Tuesday. But in particular, a query plan has a schema to it. It has a set of attributes. Those attributes have names. Those attributes have data types. And not surprisingly, the query plan class gives all of its logical plans two ways of accessing that, both through an actual schema, which is one of Spark's data types, or through a class called attribute, which is a way of referencing individual attributes in a schema. Both of those have reasons. Also, like the tree node had a way to transform all of the nodes in the expression. QueryPlan also recognizes that you might want to see an expression inside a logical plan, so it gives you a way to represent to quickly transform all of the expressions in a single node or in the node and all of its children. Okay. So relational algebra, so we'll get into these a little bit more in the coming lectures, but I really, I'll post these as well on Piazza. I really encourage you to normally I say don't look at code on the internet, but I will put pointers to a couple of specific classes that are really helpful to look at because they map pretty directly to relational algebra. And in particular, literally every single one of the operators that we have talked about so far is encoded as a logical plan. So project takes a sequence of attributes and has an input that's an input child. I mean, this is literally just a array of nodes plus its descendant in the tree. Select. Spark calls it filter. I don't blame them for that. It's a much better term, but it takes a expression and again has a child. union, you can have an n-ary union, so it takes together a bunch of children and it merges them together, and you can kind of ignore the rest of the group there. Join takes in a left-hand side, a right-hand side, and has an optional condition on it. Thank you, Darshana. Yes, so please, I'm going to link you to a couple of specific classes. Feel free to look at those, but try to keep from exploring the other part of the operator. Right. There's also a way of representing tables, and I'll get to this in the next lecture because I'm now out of time. Yeah, anyway. And one really quick note I will leave you off with here is if you've used Spark already and you're familiar with what a data frame or a data set is, there's another link here that it will essentially show you that every single thing that you can do with the dataset API links directly to logical plans. So the interesting thing here is that uh, the like if I were to take a data set and apply a filter to it on a particular condition, literally all that does is it creates a filter node in a logical plan, and it applies that to the logical plan that the data set encodes. Okay, so what I'll leave you with is that relational algebra is kind of a simple encoding of query plans. It's a simple way to think about computations over collections, and that means it maps very cleanly to how the query is going to be evaluated, but at the same time staying simple enough that we can reason about it mathematically. And that's what we'll get to next class when we talk about how we can prove that two different expressions are equivalent. I'll be around for a couple of more minutes if anyone has any final questions, but thank you, and I'll see everyone on Thursday.